Sir, excuse me, sir.
Yeah,
No,
can you hear me?
yes, sir. Yes, sir. Sir, I had sent you a mail regarding exponential learning, sir. Sir,
Correct. So I
yeah,
will I will let you know. At the end of this class, I will tell you.
sir, you have you have viewed that mail, sir.
Yes, yes, yes. I did see that email. So
Yeah,
I
sir.
will let you know.
Okay, sir. Okay, sir. Okay.
Yeah.
Yeah.
Okay. Good morning, everyone. You can hear me, right?
Good morning, sir.
Good morning.
Good morning.
Okay. So, and you are able to see the presentation as well, isn't it?
Yes, sir.
Okay, good. So in the last class, we were discussing about the types of losses associated with the fuel cell, and we discussed about activation losses in detail. So as a brief recap, what are these four losses? Activation losses, fuel crossover and internal current, ohmic losses, mass transport or concentration losses. These are the four types of losses associated with any fuel cell. And when it comes to activation losses, at the electrode electrolyte interface, reactions will take place. Because of this reactions or the rate at which these reactions take place, the voltage will vary. So always part of the voltage of the fuel cell is consumed in driving these reactions, and this loss is listed as activation loss. And in general, from an IV curve, we can make out or we can get information about activation losses. So if you split the IV curve into three zones, do we have an IV curve here? No, okay. So if we split the IV curve into three zones, the first zone speaks about the loss due to activation, and the middle zone will speak about ohmic losses or losses due to resistance. The third zone will convey information about concentration losses. And a researcher by name Toffel did many experiments with electrochemical reactions by changing the reactants. Because of those experiments, he was able to generalize that the losses due to activation follow a certain pattern, and it is different for different reaction speeds. If the reaction is slow, so a particular pattern is observed, and if the reactions are fast, so other particular pattern is observed. And this is what we discussed in the last class. And the same person came up with an equation. Two things: the theoretical part, the equation is the theoretical part, and based on the experimental results, so he came up with the Toffel plots. So Here, according to Toffel equation, this activation losses depend on two parameters. One is the exchange current density, and another one is constant A. So I naught and A are the two constants, which are the two parameters, I would say, which play a major role in activation losses. And the same Toffel equation can be expressed in terms of current as well. And in that case, it is named as Butler-Farmer equation. And impact of the exchange current density is significant. So if it is possible to keep the I naught as high as possible, the losses due to activation can be reduced. And how to bring down these activation losses? So one is increasing I naught value at cathode. So how can this be done? One is operating the fuel cell at a higher temperature. So rising cell temperature, because of that, I naught will significantly increase. If you would like to compare the operation of a fuel cell at 100 degrees centigrade with that of 800 degrees centigrade, there will be at least a 100-fold increase in I naught value. The another possibility is using more effective catalysts. So different metals, different catalysts will play a role in reducing the activation losses, and increasing the roughness of electrode is the another possibility. So what happens because of increasing the roughness? The surface area available for the reaction will increase. Increasing reactant concentration, the next possibility. For instance, we know that there are many alternatives to fuel as well as oxidant. So when it comes to fuel, if it is generated because of steam deforming, the product stream that comes out will have many other gases along with hydrogen. So in such a fuel stream where hydrogen is only a percentage, the concentration of hydrogen will be comparatively low. So instead, if you use a fuel stream which is pure hydrogen, so it will help in reducing activation losses. Likewise, at cathode, as an oxidant, ideally oxygen is required. However, air can also be used, which consists of oxygen. So because of that, the percentage of oxygen in air will be less, and that will have an impact. In order to reduce the activation loss, instead of using air, so using pure oxygen is an option. So next possibility is increasing pressure. So by operating the fuel cell at a higher pressure, occupancy of the reaction site by the reactants will increase. Because of this, to an extent, activation over voltage or loss can be brought down. So these are the possibilities by which the activation losses can be reduced. So with that, we shall proceed to the next type of loss, that is fuel crossover and or internal current. So in the beginning, I briefly explained, so what is this fuel crossover and internal current? So in a fuel cell, usually the fuel is supplied at anode, and that fuel should get consumed at anode, because of which the electrons are generated, and these electrons pass through the external circuit which is nothing but the current. For some reason, if all the fuel is not consumed at anode, or part of the fuel instead of getting consumed at anode tend to pass through the electrolyte and reach cathode, and because of the catalyst present at cathode, so this fuel will directly react with oxygen. So that means fuel is consumed. However, there is no flow of electrons through the external circuit because of this part of the fuel that is consumed at cathode, which is considered as a loss. So that is the fuel crossover part of this loss. So here fuel crossover and internal current, that means there are two components, two terms. So now we are talking about fuel crossover. So what's happening, the fuel that is supposed to be consumed at anode is passing through the electrolyte and getting consumed at cathode, because of which there is no flow of electrons through external circuit. So that is fuel crossover. And coming to the internal current part of it, ideally the electrolyte, the role or job of electrolyte is to conduct ions. So in an acid electrolyte fuel cell, it is protons. The protons that are generated at anode will pass through the electrolyte and reach cathode. So the role of electrolyte is to conduct those protons. That means only ions. However, in a practical fuel cell, this electrolyte tend to conduct few electrons as well. So the electrons that flow through the electrolyte but not through the external circuit will result in no current. So that is considered as a loss, and that is the internal current. I hope these two components are clear, the fuel crossover and internal current. So now we shall do the comparison. So essentially, this fuel crossover and internal current are equivalent, meaning if one molecule of hydrogen, instead of getting consumed at anode, if it passes through electrolyte and gets consumed at cathode, that means because of that, two electrons did not flow through the external circuit. So that is how this fuel crossover and internal current are equivalent. So first we should be able to differentiate between the two, and later we should be able to establish the relation between the two, why those two are considered as equivalent. So electrolyte will support small amounts of electron conduction. Some fuel diffuse from anode through the electrolyte cathode. Fuel reacts with oxygen in presence of catalyst, producing no current. And small amount of wasted fuel that migrates through the electrolyte is nothing but fuel crossover. Now coming to the internal current, fuel crossover and internal current are essentially equivalent. Crossover of one hydrogen molecule from anode to cathode leads to loss of two electrons in external circuit. So both are not usually of great importance in terms of operating efficiency. Okay. So now we have realized that there are four types of losses, and compared to other three types of losses, this particular loss because of fuel crossover internal current is comparatively of less importance. So magnitude wise, when we compare this loss with that of activation, ohmic or mass transport losses, so significance is little less, and also that depends on the type of fuel cell and the temperature at which it is operated. So especially in DMFC, direct methanol fuel cell, where fuel is not hydrogen. So this loss due to fuel crossover internal current is comparatively high. And it is important, its importance is much less in high temperature fuel cell because of much high exchange current density. That means while discussing about the activation losses, we realized that higher the I naught, that is exchange current density, lower the losses, and especially the fuel cells that are operated at high temperature will have high exchange current density. Because of this, the loss due to internal current and fuel crossover is also less. But in case of low temperature fuel cells, especially where fuel is not hydrogen, so it will have some impact on the open circuit voltage. So now, if you remember in the IV curve, so there was a line parallel to x-axis, that is, so IV curve is a plot of voltage versus current density. So the cell voltage on y-axis and current density on x-axis. So in such a plot, there's a line parallel to x-axis, which is known as no loss voltage. So if you consider a fuel cell that is operating close to room temperature or less than 100 degrees centigrade at ambient pressure, then this value can be 1.2 volts. However, the actual IV curve will be slightly at a lower value. So it starts at around 1 and gradually it goes up to 0.6 volts with increase in current that is being drawn out of the fuel cell. So if you take the zero current density where the initial value is 1 when compared with the no loss voltage is 1.2, so even though there is no current that is being drawn out of the fuel cell, the voltage is less. So that to an extent will speak about the internal current and fuel crossover as well. So this is about fuel crossover and internal current. So the next type of loss is ohmic loss. In a fuel cell, components such as electrodes, electrolyte, bipolar plates, interconnects, all have a specific role to play. And usually all these materials have resistance for flow of electrons and ions. So for instance, if we consider electrodes, the external circuit, the circuitry that connects the two electrodes and the load. So all these will offer certain resistance for the flow of electrons. Likewise, if we consider the electrolyte, so the electrolyte will offer resistance for flow of ions. So this resistance will result in loss of voltage. So, and it is proportional to the current that is being drawn. So which can be represented with the equation V equals IR. So I is the current that is being drawn from the fuel cell, V is the voltage, cell voltage, and R is the resistance offered. And so far, at all the places, we have expressed this current in the form of current density. So we always represent that as current density, that is current per unit area, usually unit area of the electrode. So it is either milliampere per centimeter square or ampere per centimeter square. So for that reason, so the resistance we talk about here is the area specific resistance per centimeter square of the material. And so loss due to the electrical resistance of the electrodes, resistance to the flow of ions in the electrolyte, and voltage drop is proportional to the current, so V equals IR. So with increase in current that is being drawn out of the fuel cell, the drop in voltage will also increase. In most fuel cells, the resistance is mainly caused by the electrolyte. So generally, the resistance offered by the electrolyte for the flow of ions is comparatively more. To be consistent with the other equations, the voltage loss should be expressed in terms of current density. Because of that, the resistance will be area specific resistance ASR, resistance per centimeter square of the cell or electrode. If nothing is mentioned, it is electrode. If it is anything other than electrode, then it will be clearly specified. And when current is expressed in milliampere per centimeter square, the resistance should be expressed in kilo ohms per centimeter square. So this is about ohmic loss or resistive losses. Coming to the ways by which can be reduced. So use of electrodes with highest possible conductivity. Higher the conductivity of the electrode material, lower is the associated ohmic loss. And use of appropriate materials for bipolar plates and interconnects. Depending upon the type of fuel cell, whether a bipolar plate is used or an interconnect is used. So choice of material is always a challenge and plays a very important role. By choosing the right material, the internal resistance or resistance offered for the flow of electrons can be reduced. And next is making electrolyte as thin as possible. Thinner the electrolyte, lower is the resistance offered for the flow of ions. But at the same time, this thickness of the electrolyte should not be so little that it will lead to short circuiting. So that means if the anode comes in contact with cathode because of very thin electrolyte, then it becomes an issue. So it should be thin, but at the same time, it should be thick enough so that the anode will not come in direct contact with cathode, leading to short circuit. Because of this reason, especially fuel cells such as PMFCs and SOFCs, where the electrolyte can be made as thin as possible, which will be in the order of certain microns, will bring down these losses to a maximum possible extent. And these are certain ways by which the ohmic losses can be reduced. So the next type of loss is mass transport or concentration loss. So here, as we know, the fuel is supplied at anode and oxidant is supplied at cathode. When fuel is a mixture of gases containing hydrogen, so that will certainly have an impact on the concentration of hydrogen in that mixture and the associated partial pressure. So one straightforward way of bringing down these concentration losses is using pure hydrogen and oxygen, because of which the partial pressures of hydrogen and oxygen are high. At the same time, once the reactions start taking place, there will be continuous consumption of this fuel and oxidant at anode and cathode respectively. The rate at which the fuel is consumed and the rate at which the fuel is replenished, supplied, should be same. If the rate at which the fuel or oxidant is supplied is less than the rate at which it is consumed, that will lead to concentration loss. So this could be because of the mechanism with which this fuel and oxidant is supplied. So supply of air instead of oxygen results in slight reduction in the concentration of oxygen. Extent of change in concentration depends on current being drawn. That means when the current that is being drawn out of the fuel cell increases, proportionally the consumption of hydrogen and oxygen will also increase. The fuel and oxidant will also increase. So with the same rate, it should also be supplied. How well the air around cathode can circulate, how quickly the oxygen can be replenished. Change in concentration will lead to reduction in partial pressure on both electrodes, and reduction in gas pressure will result in a reduction in voltage, which is nothing but the concentration loss. And why is it also known as mass transport loss? So it has got something to do with the transport of material, supply of material to the reaction site. So movement of mass, transfer of mass is associated. So that is why it is also known as mass transport loss. So now we learnt about the different types of losses, and all these types of losses should be measured and accounted so that the actual voltage in a working fuel cell can be measured. So the equation that you can see on the screen, so here we are trying to find out the actual voltage of a working fuel cell. So E is the no loss voltage. From that, the three different types of losses, the voltage that is lost should be taken out so that we get the actual cell voltage. So here this represents the loss due to resistance, which is represented as ohmic loss delta V OHM. So this part is activation loss, and the last one is the mass transport loss. So the next equation shows the terms that are involved. So IR, the current and resistance. So the second part is nothing but the modified form of Toffel equation. The last one speaks about the concentration loss. Okay, so E is the reversible open circuit voltage or no loss voltage. So IN, internal and fuel crossover equivalent current density. So A is the constant of the Toffel equation, and I naught is exchange current density. So here M and N are constants in mass transport over voltage equation. And R is the ASR, that is area specific resistance. So likewise, all these losses should be measured, should be differentiated and accounted so that the actual voltage of the fuel cell can be measured. So far we understood the different types of fuel cells and their working, and now we know how the efficiency of a fuel cell can be calculated and also the losses associated with it. So the next topic of interest is the reaction kinetics. So in this module 3 or unit 3, so we are left with this part, that is the reaction kinetics part. When it comes to reaction kinetics, there are again many different terms used. So electrode kinetics, activation kinetics, and reaction kinetics. So just because the reactions are involved and it has got something to do with the rate at which these reactions take place, so it is named as reaction kinetics. And it has got something to do with the activation energy, so activation kinetics, and it takes place at the electrode electrolyte interface, where the electrode has a major role to play, and the energies associated will be with respect to the position from the interface as well. So that is why the term electrode kinetics. So these three terms are used interchangeably. So essentially, we are, so in any case, whether the question is with respect to activation, electrode, or reaction kinetics, we are going to talk about the same mechanism. And coming to the questions on efficiency and irreversibility, so there may be questions in both part A as well as part B. That is quiz questions as well as the test questions. So one or two more questions there, you may have to, means you may be asked to list the efficiencies, list the types of losses, and briefly define these losses. And coming to the part B questions, so the questions may vary from 4 marks to 16 marks. So that means you may be asked to explain all 4 types of losses, and the question may carry 16 marks. Or when it is for 8 or 10 marks, you may be asked to explain just 1 or 2 types of losses. So is the case with efficiency as well. So depending upon the marks, so only the details should vary. Meaning, say suppose there is a question which carries 8 marks, and they're asking you to talk about efficiencies. Do not speak extensively about one type of efficiency and do not leave other efficiencies. Meaning, you list all 4 efficiencies until and unless they clearly specify. If they ask for intrinsic maximum efficiency, only in that case you will be talking about that particular efficiency. Otherwise, if they generalize that, describe the efficiency of a fuel cell, it is better to talk about the all 4 efficiencies, of course depending upon the marks. So even if it is 4 marks, you will just list these 4 efficiencies and just speak 1 or 2 sentences on each type of efficiency. If it is for 8 marks, so little more information on each type of efficiency. And if it is for 12 or 16 marks, give all the details that you know with respect to each type of efficiency. So is the case with the irreversibilities or losses as well. And we shall discuss the reaction kinetics in next class. Now I would like to take attendance today, so that is the first thing. Then afterwards, so there are few questions with respect to the self study, so that also I would like to clear. So let me call your names. So today is 20. Akash Tripathi, Abhipsa,
Present, sir.
Abhirup,
Present, sir.
Aditi, Aditya Anand, Aditya BS, Aditya Datta from Aerospace, Ajay B, Amrish from BT, Amulya Rao,
Present, sir.
Anirudh Sharma, Anirudh Devpura,
Present, sir.
Anuj Kumar Nigam,
Present, sir.
Anuraj, Anuraj from EC, Apurva from BT,
Present, sir.
Arijit, Arijit Banerjee from EC, Arpit Kapil, Ashutosh Agarwal
Yes, sir.
from Information Science,
Yes, sir.
Ashwin, okay, Ashwin Sudarshan, Ayush Srivastava from Computer Science,
Yes, sir.
Ayush is present, and Ayush Srivastava from EC, Ayush from EC, Basava Chetan, Bhavit Shetty, Channa Basava,
Yes,
Div-
sir.
Channa Basava is present, okay. Divyanshu Anand,
Present, sir.
Divyanshu is present, okay. Durga Prasad, Durga Prasad, Fatima,
Present, sir.
okay. Geeta
Present,
from
sir.
Computer Science, okay. Girish Gowda from IEM, Gundappa,
Yes, sir.
Harini Subramaniam, Harini is present,
Yes, sir.
okay. Himanshu, Himanshu Kalwar,
Present, sir. Present, sir.
okay. Himanshu Sharma, Rishabh Bhargava from Mechanical, Rishika Rai,
Present, sir. Present, sir.
okay. Ishita from E&I, Jayat, Jayat, yes. John Bosco from EC, Kiran K from Civil, Kushagra Kumar,
Present, sir.
Kushagra is present, okay. Kaushal,
Present.
okay. Sorry, Kushal M. Gowda, Kushal R from EC,
Present, sir. Present, sir.
okay. Sharath from Aerospace,
Present, sir.
okay. Rakshit, Rakshit Kamath from Mechanical, Mahadev R from IEM, Mahesh
Sir?
Basavaraj, who is this?
Sir?
Mahadev.
Sir, Pradeep, sir.
No, I have not called your name yet.
Okay, sir.
Okay. So Mahadev is not present. Mahesh Basavaraj, keep your microphone on mute. Mahesh Basavaraj, Mallika Gowda,
Present, sir.
okay. Mir Jasir Riaz,
Present, sir.
Mithun, Pooja, N. Pooja from Computer Science.
Yes, sir.
Okay. Nabira from Telecom. Nalin Kamal from EI. Nalin. Nandini.
Yes, sir.
Nisha.
Present, sir.
Nitya.
Present, sir.
Nitya R.
Present, sir.
Okay. Okay. Purvi from Information
Present,
Science.
sir.
Okay. Pradeep Kumar. Pradeep Kumar C from Aerospace.
Present, sir.
Okay. Prajwal Hiremat.
Present, sir.
Prajwal Hiremat.
Yes, sir. Present, sir.
Okay. And Prajwal Panchangam from IEM.
Yes, sir.
Okay. Pranav Pathak. Prasanna
Yes, sir.
Reddy.
Sir, Pranav present, sir.
Pranav is present.
Present, sir.
Prasanna is also
Sir,
present.
Prasanna present, sir.
Okay.
Yes, sir.
Praveen Khanna.
Present, sir.
Okay. Preksha. Preksha Shetty.
Present, sir.
Prerna.
Present, sir.
Okay. Mahant. R. Mahant. Rajashekar from Civil.
Yes, sir. Yes, sir.
Ronak.
Present, sir.
Ronak is present. Pranav from IEM is present. Okay. Ravi Krishna.
Present, sir.
Okay. Riya Sharma.
Present, sir.
Okay. Riza.
Present, sir.
Rohan.
Present, sir.
Darshan. Yes, Darshan. Yes, Ketan. Yes, Pavan.
Sir, Pawan present, sir.
Okay. Sadashiva. Sadashiva Hebban. Sagar Biswari.
Present, sir.
Sagar is present.
Present, sir.
Okay.
Present,
Salim. Yeah. Salim.
Present, sir.
Okay. Sandesh. Yes.
Present, sir.
Santosh T from Civil. Satyansh Singh. Sayam Agarwal. Shahid Bashir.
Yes, sir.
Sharan. Sharan C. So Shahid, keep your microphone on mute. Sheetal. Shreya.
Present, sir.
Shreya is present. Okay. Srinath L from
Present,
Civil.
sir.
Okay. Srinidhi.
Present, sir.
Yeah. Shritij.
Present, sir.
Okay. Shubham Bansal.
Present, sir.
Okay. Siddharth Prasad. Sohangi. Sohangi.
Yes, sir. Yes, sir.
Saumya.
Present, sir.
Okay. Saurabh. Saurabh Kittur. Okay. Spurti.
Present, sir.
Okay. Suvash.
Present, sir.
Suman Saurabh.
Yes, sir. Present, sir.
Tushar Agarwal.
Present, sir.
Tushar Goyal.
Present, sir.
Ujjwal Mahendru. Ujjwal Kumar.
Present, sir. Sir, but there is a issue with Siddharth microphone, sir.
Siddharth's microphone.
Sir, I'm present, sir. No, I joined in through my mobile phone. No, present, sir.
Siddharth Prasad is present. Okay.
Present.
Yes, sir. Ujjwal present, sir.
Ujjwal Kumar, right? Okay.
Yeah, sir, present, sir.
Okay, Mithun. Mithun is present. Okay, let me go back. Utkarsh. Utkarsh Kumar. Yashika.
Present, sir.
Okay. Zainab.
Present, sir.
Okay. Yeah. Thank you. And there's a question.
Sir, excuse me, sir.
Ishita.
Sir, Ishita present, sir. Sir, my microphone wasn't working that time.
Ishita. Just a minute. Okay. Ishita is present.
Sir, what about Aditya Datta from Aerospace?
So it clearly shows that you guys are just answering now. You were not there during the class and when I called your name for the first time, isn't it? What were you doing, Aditya?
Sir, I was on the laptop itself.
Then why didn't you answer?
Laptop was on low volume, sir, that time.
Very good. Yeah. Okay. And coming to Anirudh now. See, Anirudh, the
Sir.
topic that you want to work on is very generic. Okay. I don't think there is anything left to review. The one which you proposed earlier. Okay. Coming to the other two topics that you have listed. So one is direct
Ceramic
carbon
fuel
fuel cell and ceramic fuel cell. So can you be a
Yes.
little more specific on the ceramic fuel cells? Which one exactly?
Sir, actually, like when you just divided the topic on the basis of like teammates, sir, and it was like very difficult to find. So I just researched on the topics which are currently like fuel cell technologies, like recent trends in fuel cell technologies. So I came across these two topics, sir. So
See,
ceramic, yeah.
yeah, for the first point is, even though it is team, so role of every person in the team should be clearly defined, and to an extent you have to work independently. Okay, so there are two things. One is working independently as well as working as a team. So there should be a clear distinction between the two. And just because you have friends from other departments as well, if I'm right, so I just clearly define your roles. Okay, I want
So,
to
but
make
I didn't know initially that if we took teammates from other department, then it will be like distinguished because
no,
it's
no.
not
What is
happening.
the no? Now I don't understand what is the issue with that. So,
Sir,
see,
actually 50,
yeah,
50 entries, sir, it's very difficult, sir, in such a
okay,
specific.
okay. So let's take a general topic, and if we do not differentiate between the team members, how is that going to make a difference? So that clearly says that one person will find 100 papers and the other person will find 0, so that it can be split between the two. Is it how it is?
So that's why I proposed like a specific topic, sir, if that was general.
No, see, whatever is the topic, you have to clearly define the role of each candidate in the team, right? At the end of the day, so I am going to grade according to what that particular person has done. If you do not make it specific to your branch, and if you are not able to find papers on that specific topic, then it's of no use. Okay, so even if you want to work on the topic that you have proposed, either the direct carbon fuel cell or the ceramic fuel cells, so first you have to clearly tell me what is your role going to be individually for all four of you, and make it specific to your discipline. So that is very important. And coming to finding papers, on what basis are you saying that the information is not available? So please explain the way how you did the search.
So like when you just change it, like you like modified the our topic, then I just researched, sir. But it was like it's very specific, sir. Like it was
No,
mine
just a
was
minute. Just a minute. So you researched. How did you do that? Where did you
sir,
search? What did you
Google,
search
sir.
for? How much time did you spend on it?
Sir, I tried, sir, finding it, but it was it was very difficult for me, sir, to find
Anirudh,
enough material.
I do not agree with that because the very challenge here is to find the relevant information. Finding the relevant information itself is a skill. Okay, so if you can get lot of information just by spending 5 minutes on internet, it's of very little value. Okay, it has to be specific. You should struggle to find information. With that struggle, whatever you find will be helpful. Right. So if everything is available easily, tell me what is your role there?
So, frankly
Yeah.
speaking, sir, I didn't knew that it would be like divided on the basis of department. Then I would have chosen friends from other
No,
departments, CS department
no,
also, sir.
that should not make a difference to you. What I'm
Sir,
saying
it's
is,
making a difference, sir. It's making the work very, sir,
yeah,
very troublesome, sir.
no, it is not troublesome. It is difficult. I
Yes, sir.
agree. It is
Yes, sir.
purposefully defined that way. Okay. So don't think that it is a burden. So whatever you are going to learn from it is going to take you a long way. So do. It is difficult, I agree, but do it. It is
So
definitely going to
because
be
it's
helpful.
happening with one or two teams only, sir, who have made interdisciplinary, sir. Like because other teams they have made teams with the same department, so they are working on a similar
In a,
project.
in a way, I appreciate you guys because you have selected an interdisciplinary team.
No, sir, it was not, sir. It was not like on the basis of like we didn't thought that it would happen that way, sir. It will be divided.
Okay, I seriously am not able to
Uh,
make out the difference. Okay, anyways, see, at the end of the day, I tell you, so until and unless you are not able to justify that you have done some good quality work, each one of you will not get good marks, I
sir,
tell you.
like
Yeah.
sir, like also the teamwork, sir. We won't be able to help each
Yeah.
other, sir, in any way, sir, because you have
Okay.
divided me separately. I am the only CS guy in my, so I would not be able to take advantage of my team,
Okay.
sir, in any way.
Okay. So, fine. So from my viewpoint, it is an advantage. Anyways, okay. Which topic you would like to work on? So
Sir, if the distinction is not removed because it's a general topic, sir, we can go with ceramic fuel cell technology,
no, go with DCFC, direct carbon fuel cell.
direct carbon fuel cell.
Okay.
Okay, sir. Okay, sir. Yes, sir.
Yeah.
Fine.
But make sure that all of you contribute equally.
Yes, sir. Yes, sir. Sure, sir. Sir, we won't overlap, sir. We will do everything will
But
be.
at the same time, it will be very good if you can identify or if you can contribute from your discipline. Okay, fine. You however you want to work on, you go ahead, but try to find information that is specific to your discipline. As a software engineer, what is that you can contribute to fuel cells? Think in that direction.
Yes, sir. I will try finding whatever is related to my department, sir. But if
Okay.
that is very limited, then I will move on to some general.
Okay. Yeah. So this, it might be very early to say that if you do not find. Anyways,
Yes,
you
sir,
start working on
but
it.
I have to decide the topic, sir. Our team has to decide. That's why I was.
Okay. Okay. Go ahead.
So, sir, should we like just remove this topic then, sir? If because it's
Change it
like
in the spreadsheet. You just change it to DCFC, direct
okay,
carbon
sir.
fuel cell.
Yes, sir. Yes, sir. All right, sir.
Yeah. Okay. Yeah. Anything else? Okay. So if no more questions, we shall continue the discussion in the next class. Thank you.
Thank you, sir.
Yeah.
Thank you, sir.